Okay. So just a little bit about the website. The homework here is the homework problems or assignments are perhaps a little confusing because the homework problems aren't in the book. And then I've got supplemental problems. There are problems associated with the book from the author. And so, you know, if you go to, so this is my homepage, but if you click on 320, then on the lectures, again, there should be the homework assignment for that lecture period. So everyone should have turned in homework 1 already this morning or last night or sometime. Okay. And then, so homework 2, again, you'll upload to Blackboard, and it's due Monday at 8 a.m. I know 8 a.m. is a hard time because you can't come in. Well, I usually get here at 7, so you could come in and see me before class, but you know, you will probably want to look at the homework earlier in the week, ask me questions on Friday afternoon or something, or you know, I try to respond to email over the weekend to questions regarding homework, but it's often a little difficult to do that. You can certainly scan your homework, send me a copy of it by email and say, I got a question on this part or something, and we'll try and get something worked out. So the homework today, the S means it's from the supplemental set. Okay, these are problems I've come up with. Without the S, it means they're from the textbook. And then so on the homework link, you'll see both of those at the very top. These are the homework problems from the textbook. So you know, they're broken up by section and chapter. And so he didn't have any on from chapter 1, but he's got 2 problems on chapter 2. And we'll actually start chapter 2 today and then finish it on Wednesday. It's a short chapter, again, kind of an introductory chapter. So these 2 are problems, 2.2-1 and 2.4-1 are both, along with that supplemental problem, are both due next Monday. Okay, so any questions about that? Okay. So electromagnetics is what's called a field theory. And we're going to have chapter 2 is kind of a brief introduction to fields. Fields are basically functions that are functions of space and or of time. So initially, I think we'll get into chapter 4, maybe chapter 5, we'll look at what are called like static fields. So these correspond to like DC circuits where things aren't really changing with time. Our fields are constant with time. Then a little later in the course, you know, just like you did in circuits, we'll take a look at the more complex case where the fields are time varying. But they can also vary with space, okay, with where you are in space, how far you are away from a set of charged particles and things like that. And then there's 2 kinds of fields. There are what are called vector fields, and the electric field is a vector field. And there are a couple different vector fields we'll work with. The magnetic field is also a vector field. So you might see this notation. Okay. It's a function of x, y, z, the 3 spatial functions, or you may, spatial dimensions, or you may just see, you know, a point in space represented as a vector r. Again, the notation I'll use, I'll try to overline, put a bar over any vector variables. And the textbook vectors are denoted by boldface type, or sometimes just E bar. Now, the electric potential, and this is the same thing actually as voltage, and we'll talk about that, but typically in electromagnetics we use the term potential instead of voltage, is a scalar field. So, you know, kind of everyday examples of this. If you think about temperature, you know, is a function of where you are on the Earth, at your X and Y position, as well as your height above the Earth, your Z position. And of course, it varies with time, but it doesn't have direction, okay? It's an example of a scalar field. But if you think about wind velocity, same point, it varies with time, but the wind also has not only a magnitude, like temperature, but it also has a direction. So at any one point on the Earth at any particular time, you know, it might be blowing at 10 miles per hour due north, or 15 miles per hour, you know, southeast, or something like that, whereas temperature doesn't have direction. So temperature would be an example of a scalar field, whereas the wind velocity would be an example, actually, of a vector field. So in one of the homework problems, in the first homework problem, I asked you to sketch a couple of vector fields. And there's a bunch of different notations that are used for unit vectors. And right now, I'm only going to use Cartesian coordinates. So in one of the later chapters, we'll talk about coordinate systems. You know, we'll look at cylindrical and spherical coordinates. But right now, we'll just restrict ourselves to rectangular or Cartesian coordinates. And depending on the textbook you pick up, they might use I, J, and K as unit vectors in X, Y, and Z directions. This book, I think it uses X, Y, and Z with little hats over the variables to indicate a vector of unit length 1 in the Y direction. Okay, that's what this represents. An X hat would be a unit vector in the X direction. Okay. I've seen, you know, E1, E2, and E3 with hats over them, or in boldface to represent unit vectors. So here I can't really draw, you know, three-dimensional vector field, you know, in three-dimensional space. Here it's not a function of time. This is actually probably the simplest example. It's constant. It doesn't vary with space. It doesn't vary with time. And it's just fixed direction. But so what I asked you to do in the homework is draw these fields in the XY plane. But, you know, in general, they could also be a function of Z, and more generally, even a function of time. So, you know, sketching this, typically, you know, the length of the vector would correspond to the magnitude. You know, unless you lay out dimensions here, in this case, this would be dimension 2. Has a length of 2, and it's, no matter where you are, so this would correspond, all of these vectors are the same length. They would be everywhere in the plane. I just can't draw them at every point in the plane. So I just draw a few vectors to represent this vector field. So this would be the X direction. This is the Y direction. In this case, all of the vectors have a length of 2. They're all pointed in the Y direction. So this would correspond to like a wind velocity field where the wind is constant everywhere, pointing in the same direction, has the same magnitude everywhere. When they get a little more tricky, when you start varying the vector field with a spatial dimension, and here I'm only showing, you know, in general, we could have, you know, like one pointing in the positive, you know, one at x hat plus y hat would be a vector field pointing in the northeast direction at 45 degrees of length square root of 2. You get the magnitude, it's the square root of the sum of the squares of the x, y, and z coordinates. Okay, so, you know, x plus y would be pointing off at 45 degrees, constant everywhere. The vectors would all be of length square root of 2. So often when you're drawing these things, it's the relative sizes of the arrows that are important. Okay. And you've got to separate the direction from the magnitude. Okay. Here the field is always y-directed everywhere. Okay. But the length depends on where we are on this axis. At x equal to 0, it has a magnitude of 0. There are no arrows. Okay. But at x equal to 1, it has a length of 1. Okay. X equal to 1. And then everywhere on this line is x equal to 1. At x equal to 1/2, it would be half the length of the x equal 1 arrows. At x equal to 2, it would be twice as long. Okay. So the length of my arrows represents the magnitude of my vector field. And then certainly at 1.5, you can see here as you know, as I move to the right, it gets stronger and stronger. You know, this vector field, again, if you think of it as a wind velocity field, here the arrows, as long as x is it's a little challenging to draw these things, but you know, these would continue everywhere. Okay. Now for the negative x at -1, with x equal to -1, it's actually going to be pointing in the minus y direction, right? At x equal to 1, this would be e is equal to minus y. So at -1, you're going to have same length of 1 as at +1, but they'd be pointing in the negative direction. Okay. So hopefully that'll give you you know, graphically some idea of what the vector field looks like. And that's one of the real challenges of studying electromagnetics, is actually trying to visualize these vector fields. And you know, more generally, we'll be working with vector fields that are functions of x, y, and z, and maybe pointed in arbitrary, you know, have more components than just a y component. Often there you have to resort to drawing sketches of the vector fields in particular planes. Like, what's it look in the xy plane? What's it look like in the xz plane? What's it look like in the yz plane? Different projections, because we can draw them there. You know, to draw this thing in 3 dimensions with z coming out of the board, you know, I can't do that here on a 2-dimensional board. But any questions about that? I give you a couple homework problems that are a little more challenging than these problems, but it starts out, I think the first one is, the first 2 actually are constant fields. So, I'm going to talk a little bit about electric field intensity. You're going to rely some on your knowledge of physics here. I'm not going to go into any detail. This is an introduction. We'll dig very deeply into how do you calculate the electric field intensity for a given arrangement of charged particles later in this course. Okay. Right now, this is just talking generally about fields and the electric fields in particular. So assume we have charged particles QS and QT. I'm going to call these, I'm using these subscripts because they represent the source and test charges, so, or particles. Okay. And I'm going to assume that they're positively charged. Okay. Now, I think from your study of physics, you know that charges either attract or repel. So we've got two positive charges here. What are they going to be, attracted or repelled? Like charges repel. Okay. So if I held this, if I somehow held QS fixed here, I've got it glued somehow to the structure. And what direction is QT going to go? It's going to be forced directly away from QS. You know, if it's up here, it would be forced in that direction. Okay. So the force here would be in that direction. There's a force exerted on the test charge by our source charge. As a matter of fact, I can take this concept to think about, you know, Q of S actually creating a force field, okay? And I can kind of sketch what this force field looks like. I can imagine putting, you know, a test charge, you know, here, and the force I know is going to look like that. You know, if my test charge is up here, my force is going to be in that direction, or here, or here, or here. You know, ideally, if these are all at the same distance away, these are all the same length. And so I can talk about the force field of QS, and I could measure this force field by putting this small test charge anywhere in the field and measuring the force on that test charge. Now, and you probably know this as well, the force actually gets weaker the farther I am away, right? So again, based on, you know, I should have longer arrows here closer because the force will be more intense. And then smaller arrows. And this is something we'll get into much greater detail later in the course. Okay. The magnitude actually falls off as the square of the distance, like gravity. Gravity is an inverse square law. Electric field intensity, or this force field, is an inverse square law. Okay. So I'm not going to derive this, but there is an equation that gives us the magnitude and direction of this force. The force field, and this is called Coulomb's law, the force field. So I said I wasn't going to talk about spherical coordinates yet, other than the unit the radially directed unit vector, r hat. So that's a unit vector that's radially directed outward from my source particle. Okay. So no matter where I am, wherever my source is, where my test particle is, this r unit vector is in the direction from the source particle to the test particle. So that's the direction. It's directed from the source to the test particle. The force actually depends not only on how large the charge is, my source charge, but it also depends on how large my test charge is. Just like gravity depends on, you know, both masses that are involved. And then there's some constants to get our units correctly. 4 pi epsilon. Epsilon is what's called known as the permittivity. And then r is the distance from S to T, capital R. Okay. So going back, this distance would be, I could call this vector r, which has magnitude r and is in my r hat unit direction, unit vector. Okay. So r hat, unit vectors always have magnitude 1. Okay. So r is the vector that goes from the source to my test particle. And again, probably, I'm sure you saw this in, if you've taken physics 2 yet. So I know some of you may not have taken physics 2 yet, but you see this in physics 2. You probably saw it in high school physics if you got this far in high school physics. The strength of the force actually does depend on the material in which these charges are embedded. Okay. They might be in free space, they might be embedded in Teflon or polystyrene or something like that. We'll look at some sort of dielectric, we'll look at all these cases. But that's the function of this permittivity. It actually varies from material to material. Okay, different materials have different permittivities or dielectric strengths or dielectric constants. We'll take a deeper look at this in just a minute. Okay. Now, the electric field intensity due to QS is what we really want to work with is something, when we're talking about the electric field of QS, we don't really want to work directly with the force field because it depends on our test charge as well, the magnitude of our test charge. So, but we can get rid of that if we divide our force by our test charge. We get an electric field, that's independent of the test charge. It's almost, there's a one-to-one relationship between the electric field and the corresponding force field. And to get the force, we just take our electric field vector and multiply it by whatever our test charge is. It might be 1 coulomb, it might be 2 coulombs. For 2 coulombs, it's a 2 coulomb test charge. The force on that 2 coulomb test charge is going to be twice as strong as the force on a 1 coulomb test charge. But we can talk about the electric field independent of the test charge. And it has units of, well, force has, in standard units, MKS, what's the units of force? We've had newtons, and our standard unit for charge is coulombs. So the electric field has units of newtons per coulomb. The force here in standard units would be in newtons. And this would assume that the distance is measured in meters. R is in meters, Q is in coulombs. And I'll give you the units of permittivity in just a second. So this is one kind of visualization of the electric field. There's another, and we'll actually derive this later in the semester, but there's another common situation in which electric field is set up, and that's when you're dealing with a capacitor in a parallel plate capacitor. So the situation is like this. I can form a capacitor quite simply by just having two metallic plates that are separated by each other. Often there's some sort of material, it's called a dielectric material, between the two plates that will actually strengthen the capacitance. But if I put a positive voltage there, what I'll get is an accumulation of positive charge here on this plate, and an accumulation of negative charge here. So here that we'll have that voltage directly across the capacitor. It's in parallel with our voltage source. We know if this is a DC source, you know, and there's some initial current, but once the capacitor charges, there's no additional current flow. This is a distance d. We'll see later that inside the capacitor, we have a constant electric field that's set up. Where E is equal to V over D. And I'll put a little unit vector here, E hat. E hat points from the positive plate to the negative plate, directly down as I draw in this picture. I don't really care too much about the direction at this point. Know that the electric field goes from the point of higher potential to the point of lower potential. It always points in the direction of actually decreasing potential. So this sets up in a constant electric field in the capacitor. These are the other two homework problems I give you. Parallel plate are related to capacitor with D equal 1 millimeter separation. B is equal to 12 volts. Find E. Quite simply, it's just V over D in the direction from the positive plate to the negative plate, or 12 volts over 1 millimeter in the E direction. That would be 12 kilovolts per meter in the E direction. Okay, so 12,000 kilovolts per meter in the E direction would be the electric field. The magnitude of the electric field is just 12 kilovolts per meter. Note the units here of the electric field are volt per meter. Over here we got different units of newtons per coulomb. They are equivalent actually, and you can prove that he has a change of units in the text to show that 1 volt per meter is actually the same as 1 newton per coulomb. Typically, we'll use units of volts per meter most often, unless we're dealing directly with force problems. And then you may find it convenient to use the newtons per coulomb. But typically, at least in this class, when we give the units of the electric field, we'll say volts per meter. So that's equivalent over here. I could have written that as volts per meter. So they are equivalent units. Okay, I'm going to talk just briefly about this permittivity. So it's a material property. At least initially, we'll work a lot of our problems where we assume that we're working in what's called free space or a vacuum, so an outer space. It turns out that the properties of an electric field don't differ that much between free space and air. Okay, the permittivity of air is pretty close to the permittivity of free space. But the permittivity of free space here, we give it a special symbol. It's called epsilon 0. And it's 8.854 times 10 to the minus 12th farads per meter. We'll see how this is actually related to the speed of light, actually, a little bit later on. In any other material, the permittivity is going to be it can be slightly higher, sometimes much higher than the permittivity of free space. And we see with a stronger permittivity, our electric field intensity is going to decrease, right? Because it's in the numerator here. So you'll typically have your largest electric field intensities in free space. And in dielectric material, the electric field intensity will actually decrease. We're also going to pretend a lot that somehow, you know, when I'm talking about these source charges, I've got a configuration of charge. Somehow they're all glued together right now, or glued in place. Okay, we've got to pretend that that's, you know, if it's actually floating in free space, and I bring in a test charge, they're going to repel each other. Right? My source charge is going to move. But at least initially, we're dealing with these static field problems, just like you study DC circuits. Once we understand the simpler cases, we can then go on to study the more complex cases. So we'll make that assumption that our charges are typically somehow held in place. Okay. So often instead of giving the permittivity of other materials, what they give is the relative permittivity of the material. Epsilon R is the permittivity of the material over the permittivity. So it talks about what's the permittivity of this material relative to that of free space. And so the relative permittivity, those numbers will often be, you know, between 1 and 100 typically. It depends on the material. Okay. So, but they're, you know, again, usually between 1 and 100. Now, you don't plug in the relative permittivity into these formulas. You actually have to calculate the permittivity. Okay? But that's easy. Actual permittivity is just the relative permittivity times epsilon 0. You have your textbooks. You want to have your textbook. Turn to appendix A1. And I think there's a little table there. Find it for permittivities of different materials. What's the permittivity of Teflon? 2.1. Okay, now is that a relative permittivity or an absolute permittivity?
Relative.
It's a relative permittivity. Again, 2.1, and permittivity is going to be a pretty small number, actually. Relative permittivities are these numbers between 1 and, you know, typically, I don't know, what's the largest permittivity in that table? That's the largest? They don't have anything stronger than that? So maybe below the table they have permittivities of some other materials. See anything stronger?
81.
81, what's that?
Liquid water or distilled water. Sorry.
Distilled water has a permittivity of 81. So typically between, you know, 1 and 100. So the absolute permittivity here would be 2.1 times epsilon 0. So 2.1 times that 8.8. So, you know, 17 whatever times 10 minus 12. I don't have my calculator on. But so we'll see that. And again, the permittivity of air is another common case. That's about the same. It's a little greater than 1, but almost in all problems, we'll just assume that it's equal to epsilon 0, the permittivity of free space. And sometimes it's called the dielectric constant. That can be another name for it. There's one other field related to the electric field that we'll deal with in this course. It's called the electric flux density. And flux is a funny word. It's Latin for flow. Electric flux density is defined as it's the permittivity times the electric field. And this actually has units of coulombs per meter squared. It seems like there's such a simple relationship between D and E that why do we need both? You know, why don't we just always work with E? Well, I'll try to give you an argument why. In some problems, D is more fundamental than the electric field. Certainly, if we're going to start solving for forces, you probably want to work with the electric field. When we're working with electric fields between different types of material, it turns out the electric flux density is easier to work with, okay, because we have to find the electric field at the boundaries between these different materials. And that's a little easier to do when you're working with the electric flux density than the electric field. But for our simple particle, again, this formula holds if Q of the.
There's all kinds of cool information in there, awesome picture.
Hey, Mark, you're coming through on my speaker. Did I lose my speaker? Okay. I also lost my train of thought. For our simple particle, you know, Coulomb's law applies. You know, we'll deal with arrangements where we've got a charged plate and talk about, you know, the force field or the electric field above the plate, or on a charged cylinder, or on a sphere, in which case, you know, the force field, the electric field then take different points. This is really the form of the electric field for a point charge. Okay. So for our simple particle, charged particle, D is, we just get rid of the epsilon in the numerator, 4 pi r squared. And it has different units, coulombs per meter squared. Okay. Which is independent of epsilon. Okay. Now, I'll try to get really quickly, it should only take a couple minutes here, an explanation for why we work with flux density or this flow density. The flux or flow of a field through an area S is, and I'll use this Greek letter psi for the flow or flux. Notice D is the flux density or flow per area. If I multiply D by area, I'll get the amount of flow through a particular area. So again, this has applications to velocity fields, you know, fluids. You know, if I take the amount of fluid per unit area, multiply it by the area, I'll get the amount of fluid moving through that area. Okay. So, but these are vectors, so I've actually got to use, I've got an associated area with, or a vector with this area. So we'll talk more about this, but you know, if you think about the whiteboard being an area, the vector, the unit vector I associate with that is the normal to the whiteboard, the normal to my little area. Okay, so that's the vector we associate with it. Because you know, if D is directly flowing through the whiteboard, you know, I get it all. I just take the magnitude of D times the surface. But if D is flowing upwards, none of it is going through. That's why I need this dot product. If D is upwards and my vector, my unit vector for my area is outward, that dot product is 0. But if they're both flowing, if the flow is in the same direction as my unit vector for my area, I get it all. Okay, and that's why we have that dot product in there. More generally, this actually becomes an integral. You probably saw an integral like this back in Calc 3. It's a surface integral. Okay. Surface integral. Because I'll deal with a lot of surfaces that aren't flat. They're actually curved. My surface might be a sphere. So in that case, the little unit vector that's normal to my area changes depending on where I am on the sphere, right? It's always pointing perpendicularly out from the sphere. For our charge, for our particle QS, we can show, and he goes through this in the textbook, you know, it's a little bit of a review of Calculus 3, but we'll review all of that in chapter 4. The flux through a sphere of radius r is, so this is a closed surface integral, because I'm going to go around the whole sphere, so the little circle there in the integral indicates that this is a closed surface as opposed to an open surface. So plugging my formula in for D, QS 4 pi r squared dot ds. Well, I can pull QS out, it's a constant. I can pull 4 pi out. I can actually pull r out because on the surface, r is constant. Okay, I'm a fixed distance away from this particle. So it's a sphere around my particle. So r is a constant. And I'm just left with this unit vector, which is changing. You know, the unit vector in spherical coordinates actually changes direction depending on my point in space. Unlike the unit vectors in Cartesian coordinates, which were always fixed, always pointing in the x, y, and z direction. You know, as I change my location in spherical coordinates, my r vector actually changes direction. Dot ds. This is actually, and we'll look at this a little later, this is actually just the surface area. This integral is the surface area of a sphere. Okay, it's an integral over the surface of a sphere. Anyone happen to remember what that is? Surface area of a sphere? 4 pi r squared. Okay, the radius of the sphere. So we get this simple result that now this is the flux of the D field. The flux of the E field would actually be QS divided by epsilon. Okay, depend on the material. But the flux of the D field is independent of the material. It also, notice, it doesn't depend on the size of the sphere, otherwise we'd have an R in our result. Okay. So it says the flux of this D field is always equal to the amount of charge enclosed by the sphere. Okay, so it's kind of a fundamental result, but this is one of the basic reasons we often work with D instead of E, although it's easy to go back and forth. So, any questions? All right, that's it for today. We'll kind of go through this same exercise on Wednesday, looking at, there's two magnetic fields. There's the magnetic field intensity and the magnetic flux density. And then there's another constant there, it's called permeability, which is kind of like permittivity that relates the two. So we'll go through the same exercise on with magnetic fields on Wednesday, and then we'll start transmission lines on Friday. Okay, so kind of the applied portion, get into the applied portion of the course.
Thanks.